Oh, right. Thank you. So now the second talk, as I said in the beginning of the first talk, is let's say one of the three, let's call it research talks that I'm going to give. And so this first one is going to be about soft sister algebras. So mainly about the notion of softness, not only for sister algebras, but also for elements in a sister algebra. And so the aim of this project, which is jointly with Hannes Steele, really was to generalize the notion of softness that already was there for Kunz groups. So there was a notion of let's say, softness for Kunz classes. So given a positive element, you could decide whether or not its Kunz class was soft. This was a notion that had already been defined. But surprisingly, there was no sister algebraic analog of this. So given a positive element, there was no notion of that element being soft. So one of the reasons why we wanted to do this was to define, let's say, sister algebraic softness. Now, the other reason why we wanted to do this is that even though this definition, which I will give during the talk, is completely general, so you don't need any assumptions on the sister algebra to define this, it had only truly been used in the stable rank 1 case. Let's say stable rank 1. Or more generally in the residually stably finite case. And so what we also wanted to do was to provide a general definition of softness for Kunz classes. Okay, so that's, in some sense, there was this dual goal for this project. So let's say general definition of what a soft Kunz class should be. Now, why should one care about soft elements? Well, there are many reasons, but one of them is that they play a very important role in the rank problem, which is a problem that in the simple case, it's closely related to the Thoms-Vinter conjecture. So because this is supposed to be a mini course, I will now take 15 to 20 minutes to just introduce the Thoms-Vinter conjecture and its relation to the rank problem. Okay. So this is introduction. The rank problem. So, well, probably most of you have at least had the name. So conjecture. Thoms-Vinter. And what this conjecture predicts is that for a certain class of simple sister algebras, three conditions of very different flavor agree. So namely, if you have simple, separable, nuclear, unital, non-elementary, sister algebra, then, as I said, what the conjecture predicts is that three things are the same. So the following are equivalent. So what are these three things? Well, the first one is that A has finite nuclear dimension. Which I'm not going to define because it's not going to appear in the talk. The second thing is that A is that stable. And the third thing is that A has strict comparison. Now, in this context, so separate, simple and nuclear, strict comparison already appeared because then quasi-traces are traces and the talk on Tuesday already gave the definition. But in general, let me just give the definition or what at least I understand as comparison. So A has strict comparison, if x is less than y in the Kuhn semigroup, whenever x is in the ideal generated by y, so this by definition is the supremum on n of ny, and lambda of x is strictly less than lambda of y for every functional spanning out of space, such that lambda of y is finite. Okay. So recall on Tuesday we were in the exact case. So quasi traces were traces, and that's a theorem by Hagerup. And because we were also in the simple case, this condition was not here. Because in the simple case, I mean, given any two non-zero elements, one is always in the ideal of the other. Okay. So that's this extra condition. So this is, let's say, the general definition of strict comparison without assuming these conditions. Okay. No. You mean for the definition? No, 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 no. You don't need to assume it. You don't need to assume it. Okay, well, if you heard about the Thomson-Winter conjecture, then you also know that by now it's largely a theorem, meaning that all but one implication is known. So going in chronological order, by now we know the following. So we know that 2 implies 3. So Z stability implies strict comparison. In this setting, in the simple setting, this is Rotterdam from 2004. But strict comparison understood in this way follows from Z stability in pure generality. So you don't need to assume anything. A Z stable system algebra has strict comparison, because this is the same as almost non-perforation in the Kuhn series. Okay. But in the simple case, this was proved in 2004, and it predates the conjecture. It predates the, yes. What do you mean?
You're talking about strict comparison.
Yes.
We assume the algebra has a base.
No, no, I'm not assuming it.
But that's, yeah, that's the whole point of that at the bottom.
Yes, 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 exactly. That's why I'm defining it this way, because I'm not assuming that it has a base. Okay, then 1 implies 2. Again, this is going in chronological order. This is Winter, 2012. So finite nuclear dimension implies Z stability. And then
My first comment about the previous condition that you may have to put in this version of a straight comparison, you may have to assume that A is stable finite.
Why?
For example,
No, but why?
satisfied in 1, but for 2 with this definition doesn't have a straight comparison. The straight comparison for all 2 is infinity.
What? Sorry? No, because there is no trace that's finite on Y other than 0. It doesn't.
Take A to be non-zero element and B is 0 element. So, okay, by definition, so it satisfies the current condition. Therefore, RC of O2 in this definition is infinity.
No, but wait. So you say take Y to be 0?
Of the definition of.
Infinity times 0 is equal to 0.
Yeah.
So, I mean, the definition of RC of.
Yes.
Of annual funds.
Yes. But that's the
problem, right?
yeah, of course, yeah. That's why he changed it.
Right? Yeah.
He's not talking about the radius of comparison.
No.
There is talking about a straight comparison.
Yeah. Well, we can discuss this later if you will. Well, and then
We didn't discuss this once we think we agreed that when it's supposed to be larger is assumed to be non-zero. it's okay.
So here, if you write it less than or equal, yeah, I'm convinced that is true. I mean, lambda x is less than or equal to lambda y, then you have this one, but with this one, I think that. I think we have-
Okay. I don't understand your, what you're saying is right and what you're saying is wrong.
So it's the technical problem of the definition of a strict comparison.
You're looking at 102.
Yeah.
Yeah.
And I'm afraid that, for example, for O2, this definition, so, I mean, you may
Of course, lambda has to be non-zero.
Yeah.
What did it say at the very end?
That lambda y is not infinity,
This which?
not infinity.
Okay, but you also want to exclude the
Yeah, but
lambda equals 0.
in some sense, it's excluded here, no? Because it's,
Well, well, it,
well, okay, let's say,
that means that would never hold, that would never hold for any,
Then-
that would never hold.
yeah, okay, let's say the lambda is non-zero then.
Yeah, well, that's necessary. I think.
Yeah, yeah, yeah.
But then if the lambda is non-zero, and then if the larger element is supposed to be larger, is assumed to be non-zero. And then I think this is probably okay. And then that's what well, alternatively, you can say that if the y is 0, then the x is 0, and that's what the first thing says.
Hmm.
So what I'm saying that instead of lambda is strictly less than lambda y, so here you should add lambda of x is less than or equal.
No, then that's false. Yeah, yeah,
You have to, do not have to.
The strict comparison, oh, that's where the word strict comes from.
yeah.
No, but where do you think this word strict came in? That's the only place where it's strict comes from.
If the relation is less or equal to, then.
If,
Yeah,
okay, if you really want this, I can put a less than or equal here. So this is the same as saying that lambda of x is less than or equal to lambda of y for every lambda.
Well, let's postpone it to another occasion.
Yes.
But maybe the question will come up again.
Yeah, okay. So, well, anyway, so where was I? Yes, 1 implies 2, 2 implies 1. This is Castillejos, Ebbington, Equisis, White, Winter, and this is, I think, 2021. Okay, so we know that 1 and 2 are equivalent and that either of those implies strict comparison. So all that's left to prove is that strict comparison implies 1, or equivalently, that strict comparison implies that stability. Okay, so what is left is, let's say 3 implies 2. And what I wanted to say is that there is a way of approaching this using the Kuhn group explicitly. So of course, any approach will use it implicitly because strict comparison can be defined using the Kuhn group. But there is an explicit approach which is given by the ranks problem. Okay. So now, how can one approach this? Well, first of all, looking at that stability of the system algebra under certain minor assumptions is the same as looking at the Kuhn group of A being isomorphic to the Kuhn group of A tensor to Z. So what this says is that if you have a simple separable unital system algebra of locally finite nuclear dimension, which means that every finite set is contained in a subsystem algebra of finite nuclear dimension, then A is that stable if only if the Kuhn group of A is isomorphic to the Kuhn group of A tensor Z. Now, if you want to prove this, as I was saying, there is a way of doing this by trying to solve this so-called ranks problem. And so what's that? Well, the ranks problem is really a very natural question if you think of vector spaces. So let's say that you have a vector space, then you can create its dual, then you can produce its double dual. Right? Then given an element X, there is a natural way of sending it to its double dual, which is just given by the rank map. So this takes a functional, so an element in the dual, and evaluates it on X. Okay. Now, by basic linear algebra results, this map is an isomorphism. So in particular, it's injective and surjective. Now, the ranks problem, and also strip comparison in some sense, asks what happens if we change B for a Kuhn semigroup. So let's now take this out and let's change it for Cu of A. Right? And each dual, in some sense, is the set of functionals on the Kuhn semigroup, which is that over there. Sorry? Right, yeah. So f of Cu of A can be seen as the dual of the Kuhn semigroup in the sense that it's something that sends Cu of A to 0 infinity. So it's maps that send Cu of A to 0 infinity. So in some sense, you can think of it as the dual. Right? And now the double dual is something which I'm going to define. That's denoted by L of f of Cu of A. Again, this is something that I'm going to define. Now, it will follow from the definition that if you start with any element X, then this map here will still be here. Okay. So any rank of an element in the Kuhn semigroup is going to be an element here. And now, in the vector space case, this was surjective. But when we change this for Kuhn semigroups, this is no longer the case, at least not in general. And what the rank problem asks is when this map is surjective. So that's the rank problem. And in a very weak sense, strict comparison is saying that this map is injective in some interpretation. Okay. So now the way to construct this double dual is to start with this. So this is the same definition, but now instead of n union infinity, we have 0 infinity. And instead of having a topological space, oops, you have this, which is, again, a compact Hausdorff space, not metric, but still. And then you define inside of this L of f of Cu of A to be the smallest sub Cu semigroup, or well, yeah, let me just write it this way. So the smallest Cu semigroup that you can find inside here, which contains these things. So, yeah, go ahead. Oh, okay. So you can produce rank maps. Then, as simply functions, you can multiply them by rational numbers. And then you look at the smallest Cu semigroup inside here that contains these things. And that's L of f of Cu of A. And introducing this correctly would take a whole talk, because this ends up being a tensor product of Cu of A by something. And there is a theory of tensor products for Kuhn semigroups. But again, I'm not going to discuss this. All I wanted to say is that that map is at least well defined. So if you start with an element X, the rank map lives here. Okay, and the question, and this is the rank problem, which makes sense for possibly non-simple system algebras. So this is not restricted to the simple case, is this. So is X to X hat surjective? So mainly, when do we have the same as in linear algebra? So what's the connection between this problem and that stability? Well, the connection is that in that setting, they are the same thing. So this is the theorem. And in 2012. So under the same conditions, so let A be a simple, separable, unital with locally finite nuclear dimension. Then the following are equivalent. So Kuhn semiloop of A, the Kuhn semiloop of A tens of Z, which by the previous theorem is the same thing as A being isomorphic to, or so A being Z stable, sorry. The second thing is that the Kuhn semiloop is almost divisible. And this I will hide, sorry, assume that A has strict comparison, otherwise. And this I will hide. Well, I'm trying to go from 3 to 2 in some sense. So, and this, I mean, really, the formal statement of this is that this is the same as this being almost divisible and almost unperforated, which is the same thing as the comparison. And then the 3 is that this map is surjective. Proving surjectivity of this map, modulo locally finite nuclear dimension, is the same thing as proving Z stability of the algebra. And there is no known simple separable unital nuclear non-elementary system algebra that does not have locally finite nuclear dimension. Okay, so this is the relation between the rank problem and Z stability of the system algebra. But where do soft elements come in? Well, they appear when you're trying to realize ranks. So when you're trying to prove that every element in the double dual is a rank. So rather recently, Hill showed or proved that the rank problem has an affirmative solution when the system algebra is simple and of a stable rank 1. And then it was extended to the non-simple case, or to the, let's say, to the non-simple case, and as much as you can extend the result by Antoine Pereira, Robert, and Hill. So what they showed in the non-simple case, but which includes, of course, the simple setting, is the following. So let A be a stable rank 1 system algebra, and assume that the system algebra is sufficiently non-commutative. So assume that A has no non-zero elementary meaning isomorphic to K of H. So it has no non-zero elementary ideal quotients. And this is a family that will appear on Tuesday, so I'm not going to say much about it. But under these assumptions, then this map is surjective. So in particular, for simple non-elementary sister algebras, the rank map is solved. Because in a simple sister algebra, the only non-zero elementary ideal quotient is the sister algebra itself.
No, there's one more character you could say, yeah, so you just said ideals of quotients, then that would be
Yeah.
a formal way of saying it, and this is fine.
Yeah. Yes. Yeah. So it's
Well,
or the question of an ideal.
yeah, so whether you say ideal or ideal, that doesn't matter, yeah, it's fine, I like it. This is but I like to see something correct if possible.
Okay.
I think if convenient, then why not do it correct?
Okay. Well, then, yeah. So under these conditions, this is surjective and soft elements appear here. And for every element in the Kuhn semigroup, the rank map is actually, I mean, the rank map of a soft element. Okay. So at long last, we make it into soft elements. Yes. Yes. This is what comes right after this. Yeah. So what's a soft element?
Definition of soft, are you going to define soft?
I'm going to right now. Yes. Yeah. All right, I'm going to give the old definition first, and then I will give the new definition. Okay. Now, what's the old definition of softness? Well, this is well defined by Antoine Pereira and Thiel. And I'll just give you the definition for CU semigroups, but if you will, you can specialize it to Kuhn semigroups. So X in S is soft if whenever X prime in S satisfies X prime compactly contained in X, there exists some K natural number such that P plus 1 X prime is less than K times X. Okay. So informally, what this means is that every element compactly contained in X is actually much smaller than X. Why? Because usually you could only get K times X prime less than K times X. But in here, what I'm saying is that I can actually sneak in an extra copy of X prime.
That's not equivalent.
To what?
Well, the two things are not equivalent.
Which two things?
Well, you got two properties of X. Well, anyway, okay, good question. If you have X prime and X given, then you've got two relations, two possible relations between them. One
Yes.
is, one is compactly contained, and the other is
And the other is this one.
if you have this, okay, and you
Softness means that this implies this.
okay, so the soft means the first implies the second.
Yes, exactly.
Right. But does the second, when does the second imply the first? I guess not,
Not always.
no,
But-
no, of course not, but But if it, no, for instance, if they're both infinite, they're both the infinite element.
then they are then that's not
The
true.
infinite element is not compact.
Exactly. Yes. So that's an example. So let me just guide it. So if you take x to be infinity y, something like this, then x is soft in this sense. Simply because it's already infinity, so it is still x. So this is soft. Okay. So now, as I said, this definition works really well when you assume some sort of cancellation, so meaning stable rank 1, let's say. But as soon as you don't assume that, then these elements don't really behave that well. And so one wants to give a new definition of this. And I will give two. One that's, as I said, sister algebraic, and the other one which is like in the Kunz group. Okay. Now, what's the soft sister algebra? Well, definition, an element is soft. Let's just, we have a definition for general elements, but let me just specialize to positive elements. A is soft if no quotient of the hereditary subsister algebra is unital. No non-zero quotient. So that's the definition. Examples. First of all, a projection is never soft unless it's zero. So P is soft if only if P is zero. Simply because the hereditary subsister algebra is unital itself. So you have no hope. And an affirmative example is that any soft element, any stable element is soft. So A is stable, A in A plus stable implies that A is soft. Now, one says that an element is stable, and this is a definition that has been around for a while, if the hereditary subsister algebra is stable. And such elements cannot have a hereditary subsister algebra with a non-zero unital quotient. So in particular, they are soft. Now, let me give the Kunz theoretic definition, and then I will make the link between the two. So strongly soft Kunz classes. We want, as I said, to give a new definition of softness that recovers the old one in the stable rank 1 case, so that we don't lose the results, but that it behaves better in the other settings. So the definition that we came up with is the following. So X in S is strongly soft if whenever X prime is way below X, so as before, there exists some element T in S such that X prime plus T is less than X, and this is in the ideal generated by T. So this is the, let's say, the strong definition of softness, or the strong notion of softness. Again, the underlying idea is the same, which is that if you have something that's compactly contained in X, then that thing is much smaller than X. And this is witnessed here. So if X prime is compactly contained in X, this means by definition that you can put some element here in such a way that this element is still large, in the sense that X is in the ideal generated by T. Okay. So that's the underlying idea of this definition. And then, well, first of all, what one can show is that if A has stable rank 1, an element is soft if only if its class is soft, if only if its class is strongly soft. So everything coincides in the, let's say, in the setting where things have already been done. Okay. So now, what's the general relation between these elements? Well, one can show that strong softness always implies softness in any setting, and that's where the name comes from. And now, the other relation is that in a general sister algebra, if you have A in A class, then A being soft implies that the Kunz class is strongly soft. And if the class is strongly soft, we don't know in general, though we don't know in many cases, but in general, we don't know that this implies that the representative is soft. That we do not know, but presumably it's true. But what we don't know is this. So if A is strongly soft, so this implies that for every positive epsilon, you can find some B soft in the sister sense that's full, so such that A minus epsilon positive is in the ideal generated by B. Now the question is, and again, we don't know this in general, but we do have many cases, if this implies that A is equivalent to B in B soft. This we do not know. In some cases we do. Okay. It's not true that A, the class of A being strongly soft, implies that A is soft. For instance, you can take a purely infinite projection, and you can see that the class is strongly soft, although the projection is not soft. But in general, you have this.
But if the algebra has stable rank 1.
Then everything is the same.
Well, okay, but I have a question. Suppose that you're talking about a stable rank 1.
Yes.
But then it's true that for the classes, the Kunz classes of elements, they're soft if and only if they're strongly soft.
Yes.
Okay, but could this possibly imply that the C-square algebra is stable rank 1?
I don't know. No. I don't know. In this way, no.
Well,
But if the actual element is soft, then I don't know. So I mean, there are two. So there is this question.
okay, but I find that semi-group condition.
I know. Yeah. But I mean, so this is one question, and then your question is, if I understand it correctly, that this would imply that A itself is soft.
Correct.
You're asking when this implies that A itself is soft, right? That's what you're.
I don't think it's the same.
It's not the same question. No, no.
You know, maybe that's a good question, but I don't think that was my question. I think the question was nothing to do with elements of the algebra. Except just the vertical being dense. Okay.
Right.
And so well, of course, you can put some other conditions on the functioning group too. But here's one I hadn't thought of before, assuming the strongly soft and soft in the city.
Yeah, I see what you mean. No, because for if your system algebra is stably finite.
Well,
Then-
right, by the way, if you look at the infinite element, is that strongly soft?
Yeah.
It is, okay.
Yeah,
good.
yeah. But if your system algebra is stably finite, then strongly soft and soft are the same thing.
Yeah.
So you don't need stable rank one.
Oh, okay, but that's, I don't suppose that's it, no.
No,
Not-
no. Okay. So why is one interested in these sort of things? Well, in the context of the rank problem, the rank problem only has a positive solution. So if you assume that the rank problem has a positive solution, sorry, then this must imply that you have many soft elements. And so this is the following definition. So let's say that a system algebra A has an abundance of soft elements if essentially that thing happens. So if for every positive element and positive epsilon that exists B in here, that's soft and that's almost fault. So soft and such that A minus epsilon positive is in the ideal generated by this soft element. Now, as I said, and there are some technical conditions, but essentially the rank problem having an affirmative solution almost requires this to happen somehow. Yes.
But if algebras never have abundance.
No, never. Yeah, never. In particular, this implies that no non-zero ideal of a quotient is elementary. So this implies that. So
Mean by span of, okay.
the ideal generated by B,
The
it's
ideal-
generated by B. It's
So, but, it's already, if you interpret that in a natural way, I mean, I thought that ABA was you don't take some elements, well, okay, anyway, no, you just take a single element from it. So originally, it would be.
right. Yeah.
Well,
No. So okay, now what happens under this assumption essentially? Well, one can prove that if you have a system algebra, so then the following are equivalent. So the first thing is that A has an abundance of soft elements. The second thing is that A has what's called the global Klein property, which I'm just going to define here. So what this means is the same definition here, but instead of B soft, you want B to be square 0. So for every A in A plus and positive epsilon, that exists
In terms of the continuity.
this condition.
No, we run this. So
Yes, it's the same as, yes, exactly. Yeah. So there exists this such that it's square 0 and A minus epsilon plus the same thing. Okay. So having an abundance of soft elements is the same modulo a Kuhn-Semirup condition that I'm hiding. Is the same thing as having an abundance of nilpotent or square 0 elements.
The ideal generator to R.
Yeah.
We need to put R star in it.
No. What?
That's how it seems algebra.
Oh, that's true. Yeah. You do need to put it. Sorry. Yeah.
I'm sorry.
Yeah. You do need to put it. Yes.
Put it R star.
Yeah. So now, just to finish the talk, let me go back to the rank problem, which was the whole purpose of the introduction of these elements. Now, if A has that property, so the global Klein property, and this, I said this, but I didn't add this. So there is also a, let's say, a CU condition, which presumably can be dropped, but let's just say if A has the global Klein property, then first of all, for any element in the Kuhn-Semirup, the rank of this element is the rank of a class whose representative is soft. So when you try to prove the rank problem in full generality, you can restrict your attention to soft elements. Then in particular, this also implies that the quasi-traces on A, which again are identified with the functionals on the Kuhn-Semirup, this is the same as looking at the set of soft elements. So quasi-traces are determined by soft elements. And because of this, then you can also see that the radius of comparison, let's say the algebraic version of it, which is using the Kuhn-Semirup, is the same as the radius of comparison of its soft part. So you can restrict also this computation to the case of soft elements. And you can also prove, but this notion I will introduce on Tuesday, that the dimension of the Kuhn-Semirup, this is bounded by the dimension of its soft part plus 1. So whenever it makes sense to talk about the rank problem, which is conjectured to be the same as the case of the global Klein property, then you can always restrict your study of ranks to the study of soft ranks, which is what happened in the stable rank 1 case, but now we do not need that assumption. And so, well, that's all I wanted to say.